2 years ago, I came here ready to present on the new map we produced for the southwest Yilgarn craton. And since then, we've acquired a lot of new data in the southwest and in the West Yilgarn in general, particularly with the acquisition of 3 deep crustal seismic lines, and as many others have talked about it today as well, the data that is just being released from the WRA project. So today we'll mostly talk about some updates on our understanding of the geology of the southwest Yilgarn, and talk about the crustal architecture of the West Yilgarn in general, based on these new geophysical datasets. So the West Yilgarn project, the West Yilgarn is the portion of the Yilgarn craton that is exposed to the west of the Eastern Goldfields superterrane. And we divide it into 3 terrains. We've got the narrower terrain to the north, then the UNME terrain that forms the main part of the West Yilgarn, and the southwest terrain through here. The whole West Yilgarn has been affected by Proterozoic modifications on its margins, and it's bounded by the Capricorn orogen to the north, by the Pinjarra orogen to the west, and the Albany-Fraser orogen in the south. So why looking at the West Yilgarn is relevant also to you guys is that we start to have more and more compelling evidence that the UNME terrain underlies the Eastern Goldfield superterrane, as is shown here on this diagram by Mazurel et al. 2022, and as Jyotindra as well was showing earlier today. And it forms the substratum over which the Eastern Goldfields developed. So understanding the UNME terrain might help also understanding the evolution of the Eastern Goldfields superterrane. So as an introduction, I just want to start again where we stopped 2 years ago when I came to present this map. So we produced this map for the Southwest Yilgarn. This was a complete new interpretation, and one of the main outcome of this mapping was the redefinition of the boundary between the Southwest terrain and the UNME terrain. And the previous location of the boundary was previously proposed to follow that gray line through here, and we moved it by about 200 kilometers towards the southwest along that red line here. We've also identified in this mapping what we refer to as the corriging tectonic zone that sits directly against the new proposed terrain boundary. So back then, one of the arguments for the redefinition of the boundary was the geochronological argument, in which we could not identify or didn't know from the published geochron data. It seems that the southwest terrain did not contain these old rocks that are well characterized in the UNME terrain. However, we knew from from unpublished geochronology data and from the isotopic data as well, there was we sort of knew that there was likely some really old basement components as well in the southwest terrain. So we now have a more robust geochronology for the southwest terrain, and it shows that we need to update that time-space plot that I was showing on the previous slide. We found in the southwest terrain 2.839 MA granite gneiss, and we found also in the UNME terrain some really old rocks as well, dated at 3.275. And a collaborative work with CET through the PhD project with Kat Gill here. She's found some really old basement rocks in the 2J region of the southwest terrain, with granite crystallization ages, protolith ages to the gneisses, dating at least as far back as 3.4 GA and 3.2 GA. And there's another study by Kirkland et al. Where they found a xenocrystic zircon preserved in a Proterozoic dike, and the xenocrystic zircon returned a crystallization age of 3.44 GA. So if we put that on this extended time-space plot, it looks like we've got much older rocks than previously thought in the southwest terrain. And I've plotted here to the right as well the ages for the narrower terrain, and whilst correlations between the old ages that we now find in the southwest terrain and the UNB terrain are tentative with those of the narrower terrain, it's not really conclusive just at present based on the current data. Anyway, during the last 2 years, we've also refined our understanding of the corriging tectonic zone. And I'm showing here the ductile architecture of the southwest Yilgarn, here shown by the foliation trajectory map, and I'm plotting just the ductile shear zones. The colored polygons here represent the various tectonometamorphic domains, and the corriging tectonic zone is the one marked by the blue polygon in through here in the middle of the map. I'm also showing on this map the various dots that you can see there. They are the Archean peak medium pressures and metamorphic ages that we have for the southwest. And based on this mapping, we can interpret that the corriging tectonic zone is a sinistral transpressive orogen that formed in the hanging wall of the terrain boundary, and with peak metamorphic conditions of about 5.5 kilobars to 6.5 kilobars, temperatures of 750 to 850 degrees C, all that attained at about 2665 to 2635 MA. So if we draw cross-sections across the corriging tectonic zone, they would look a bit like this. So here I'm showing two cross-sections from A to B and C to D. These are this one and this one. And these are crustal scale cross-sections. They are idealized cross-sections, and I can show on the map in here, which is a bit different colors to the previous one, the purple, yellow, and green colors are the supracrustal rocks. We've got in the blue colors, we've got the high calcium granites. With the deeper blue color, the granites, the high calcium granites with high strontium-yttrium ratios. And then I show on this map the pink and red colors. They are the low calcium granites and low calcium high titanium granites. And on this cross-section, we can see how we interpret the structural and the crustal architecture of the corriging tectonic zone, which we interpret as a thrust imbricate system that allows the exhumation of the mid-pressure granular facies rocks of the southern UNB terrain, thrusted over the southwest terrain. So this tectonic style that we see for the corriging tectonic zone is very different to what we see elsewhere in the Yilgarn craton, in the sense that the corriging tectonic zone forms that wide belt, about 100 to 150 kilometers wide belt of parallel shear zones. So it shows a good strain localization in an orogenic belt, which differs quite markedly from the map pattern that we see in the northern UNB terrain and elsewhere further east in the eastern goldfields, where we have a more distributed network of shear zones distributed over the whole terrain scale. Well, here we have a really well localized deformation belt for the case of the corriging tectonic zone. So that deformation style that is quite unique to in the Yilgarn craton, looking at this publication from Kanya et al. 2011, we would make the correspondence between this type of deformation and with a relatively good strain localization, a bit similar to what they portray here for what they call the mixed orogens. And they show in this diagram that we went from in the Archean in general, from this classic dome and keel type of architecture to shear zones, to deformation with no strain localization, to better localization, and eventually the modern day examples of these cold orogens with a lot of strain localization. And in this diagram, they sort of explain it that this is a change through geological time, through Earth history, that we can go from these buoyancy-driven tectonics to now the subduction-driven tectonics in the modern days. Anyway, all these interpretations we had for the Southwest, we've acquired active seismic data along this line. This is one of the 3 seismic lines we've acquired in the West Yilgarn. This is the longest one. It's about 650 kilometers long. It goes from the Albany Fraser here in the east all the way to the coast to the west. And this is just a fantastic opportunity to test the interpretations of the map that I've just presented for the last few slides. We see in the section the moho is really well sharp and well defined in the east and becomes more fuzzy towards the west. We see it sinking down to some great depths in through here, and it becomes quite diffuse towards the western margin of the craton, where it's really shown just as a different color contrast between the crust and the upper mantle. So this would be our interpreted moho. We see the terrain boundary. If you drop it down through here, there will be a structure that goes in through here. We see a series of structures that are west verging structures as we interpret it from the mapping and that explains also the exhumation of the mid-crustal rocks of the southern UNME terrain over the southwest terrain. And we interpret the crustal root that forms underneath the exhumed rocks of the southern UNME terrain to result from crustal stacking in the mid-crust region of the southwest terrain. We have a really fuzzy zone in through here, which I will not talk about in detail in through here, but these are probably due to Proterozoic modifications of the craton margin. So if we look just at the crustal thickness based on the active source data, and let's try and compare it with the WRA passive seismic data. On the top right-hand corner, Ruth and Klaus have already shown this map. This is interpolated single station H-kappa method that shows that the depth of the crustal thickness at each station, interpolated between stations. And in this plot in through here, this is the receiver function CCP model, which shows velocity variations within the crust and upper mantle, and the blue colors in through here should map the moho. The thick black line in through here is derived from this map here on the top right-hand corner. So we see some correlations. So the scale is not exactly the same on the active source data and on the passive source data. I go down to 50 kilometers in through here. So I interpret a moho that goes down to a maximum of 50 kilometers based on the active source data. And the passive source data here, we go down to 60 kilometers in through here. So if we go directly against, we could interpret a moho based on the CCP model that goes down to about 45 kilometers as well. The general shape of the moho seems to correlate well with the active source data. We have something that goes up a little bit and then sinks down and then goes back up and then into a region that is a bit complicated, maybe complicated by the Proterozoic. Again, just to reiterate how important these data sets are, and Klaus has already made this comparison, but there is, if we look at the crustal thickness versus the granite trends from Hughes' geology paper, what this really indicates as well is that there is a clear northeast trending architecture for the base of the crust and the moho, which is decoupled from the north-northwest tracking upper crustal architecture that we know of for the rest of the Yilgarn. But now if we look even deeper and compare the moho topography shown here, again with the mantle architecture, we can see a potential correlation between the crustal architecture and at that slice at 80 kilometers depth. But clearly there's no more correlations between the base of the lithosphere architecture and the base of the crust. However, there is a potential correlation that we are trying to make with the upper crustal signature and the topography in the LAB. So you must have an LAB that the trends in the LAB dissected by trends in the lower crust, and the trends in the LAB somewhat manage to affect again the upper crustal architecture. So that's something we are thinking about. In addition to the Southwest 1 line, we've also acquired an extra 2 lines in the West Yilgarn. This is Midwest 1 is the northernmost one, and Midwest 2 in here. And these are the corresponding seismic lines. On the northernmost line, MW1, we see a really sharp moho, followed to the west by a more diffuse moho and becoming near absent or really diffuse under the Perth Basin. And we have a pretty similar scenario for MW2, where at a similar location, we also have a diffuse moho and then going really diffuse under the Perth Basin. And this shares similarities as well. The moho characteristics share similarities with what we saw on the Southwest 1 line. We also see a deepening of the moho in Midwest 2, which we don't really see in the same location on Midwest 1. Something else that is really striking when we look at Midwest 1 is the stark contrast in seismic character of the lower crust along strike. We go from a really highly reflective lower crust with subhorizontal to gently west dipping reflectors in through here to a seismic character that is really widely different on the other side. And from the mapping, we know that here this is Yilgarn, and to the west of it there's the Yilgarn Dome, and west of the Yilgarn Dome we see also evidence for other dome structures. And while to the east of the Yilgarn Dome the geology is quite different, and it's marked by, just going to show it in through here. So this is Yilgarn in through here and then going towards Magnet towards the west, and the east of Yilgarn will be all dominated by these distributed high strain zones, transpressional high strain zones, these north strain zones. So on either side of the Yilgarn Dome, we've got a very, very different signature that is really well imaged in the seismic data. In Midwest 2, we see this well-imaged thrust imbricate system, which also indicates a much stronger crust and shows good, strong localization. And crustal thickening processes also so comparable to the type of deformation pattern that we see along the Southwest 1 line. Looking at the passive seismic data along Midwest 2, it shows a moho that is in better correlation with the CCP model and the active source data than it is with the H-kappa method. And something else that is quite striking from the Midwest 1 line is that this is the first time that we have reflectors that dip to the west in the mid and lower crust regions, while you know from the UNB lines, all the architecture is dipping to the east, and this is the same as well for the Eastern Goldfields lines. This is something that is happening then around McMagnet. On either side of it, east dipping reflectors to the side and west dipping reflectors to the west. We do not have passive seismic data yet to cover the Midwest 1 line, but this will come during phase 2 of the WA array, and so watch this space. And so just to summarize, I just want to say that the West Yilgarn has it all, or almost. From preservation of an architecture that we may think is due to the preservation of buoyancy-driven tectonics. And then on the eastern side of Yilgarn, we've got the preservation of a very different tectonic style, which is that of this distributed shear zone pattern that we know of the northern mid-terrain and eastern Goldfield superterrain. While in Midwest 2 and Southwest 1, we show a tectonic style that is very different and shown by strain localization in orogenic belts. And so when in this diagram they were showing this type of differences in tectonic style through geological time, we are seeing these changes in tectonic style over a time window that is shown here by this red rectangle, just in 300 million years. So we cannot be looking at processes that are worldwide processes, such as decreasing in mental temperatures, to explain that we have three tectonic styles basically simultaneously. But maybe we're looking more into progressive localized cratonization processes to explain this very different drastic change in tectonic style across the West Yilgarn. And that's it. Thank you.